Hello everyone, thank you for watching this presentation. Today I'm going to talk about a project I'm developing this year. It is called Computational Characterization of Salsa Music. This project aims at performing a data mining process to a data set of salsa songs to discover patterns in salsa music and thus to provide a definition of what salsa is. But before I get into the project, I want to show you the road that I have walked to this project. I come from here, Colombia. Specifically, I come from a city called Cali. It is a beautiful city, a lot of places to visit, a lot of green places. I work at this university, Pontificia Universidad Javeriana. It is located at the south of Cali. It is a small university. It has 19 undergraduate programs and 23 graduate programs. Early next year, we will launch our first PhD program. The university counts with almost 7,000 active students and 800 faculty members. In addition, this was the university where I studied. I studied computer science, and during my studies, I had the privilege of meeting Camilo Rueda, a professor which combines two of my passions, programming and music. He showed me the way to my undergraduate thesis project, which was this, Open Music for Linux. You see, Open Music is a programming language for music. This means that the outcome of the execution of programs is a music structure. It was developed at IRCAM, the Institut de Recherche et Coordination Acoustique Musique in Paris. But at that time, it was developed only for Mac OS. Since at that time I was in the open source group, I came up with the idea of developing the Linux version of this language. I implemented only the kernel of OpenMusic, and the people at IRCAM liked the software and invited me to work with them. I lived in Paris for a year, and my work was part of the ACNULA project. The OpenMusic project was in the line of the Avispa research team. Avispa is a research team aiming at developing formalisms and tools for modeling and solving real problems in areas such as distributed systems, system biology, computer security, and computer music. At the same time OpenMusic was developed, Avispa also developed its own version of a programming language for music. It was called Cordial, and it was conceived to be closely related to a computational calculus called Pico. This calculus was the first calculus integrating objects and constraints, and it was built for solving musical problems. However, it has some problems. For example, it lacks important notions in music such as time. I was part of this project, so this gave me the idea of what I want to do in my PhD. So my dissertation was about a process calculus called RTCC. This calculus is based on CCP, that is the concurrent constraint programming family. It supports true concurrency, it has a metrical notion of time. In this calculus, we can bound the execution time of a process. Unlike other calculi on the same family, this one has a transition system with resource handling. That is, other calculi assume that if we have 1,000 processes to execute concurrently, then there are 1,000 processors to execute them. In RTCC, we specify how many processors are to execute all processes. In addition, the RTC calculus has the notational semantics based on shoe spaces. This is a novelty in the history of process calculi, never tried before. And finally, it comes with real-time logic to prove properties in the process model. Here, there are two examples of the use of this calculus. First, we model a particular feature of OpenMusic called maquettes. Maquettes are musical structures where temporal objects are organized chronologically. We model them as processes where all temporal objects are executed in parallel, along with the Allen's relations between time intervals. The Allen relations were defined as constraints. Each temporal object is defined as a process that will perform something when the clock reaches its starting time, and it will execute it until the clock reaches its ending time. That something can be, for example, playing a note or a chord, something like that. So in order to take into account the time, we define a discrete clock and launch the system executing the maquette and starting the clock in zero. Another example we model was the notion of dissonance. Dissonances are used in music to direct the harmony in a composition. They are processes consisting in a series of cycles, tension, relaxation. This cycle is generally seen as the flow preparation, dissonance, and resolution. We model the cycle in RTCC. We assume there is a conductor giving signals to each one of the stages in the cycle, and musicians are always watching for these signals. When one signal is given, the cycle changes its stage. This is executed until reaching the resolution process. Okay, after I finished my doctoral studies, I wanted to explore more practical formalisms. We proposed a model for composing pieces of Johann Sebastian Bach using stochastic context-free grammars. This model consists in three processes: a progression generator, a rhythm generator, and a note assigner. They were executed with some initial parameters such as tonality, measure, sets of rhythm and notes, etc. And they follow this grammar. These grammar were built after analyzing some pieces of Bach. Since not all pieces were the same, we calculate the probabilities of each terminal and non-terminal symbols of the grammar. I also explored the use of constraint programming in music. We built a constraint system in the Mozart language. It was a simple constraint system just for harmony. Music relations were implemented as propagators. In this example here, we implemented the elementary problem of finding a chord of three notes. The chord must be in the C major scale. It must include the note C, but it can't have the note G or the note E. At the right, you can see the search tree. There are four solutions to these problems. After this exploration with the acquired knowledge, I wanted to do something more challenging and useful. So we came up with the idea of developing a music search engine. We wanted to develop a search engine like Google, but specialized in music. However, we want to be like Shazam or Soundhound. We want to solve text queries like I'm looking for a song similar to that songs of this band. I remember he has a guitar and at the end there was a splash. Psh. Okay, it was a good idea. So we needed to develop two models. First, we needed to find an efficient way to storage the information about the songs. And then we needed to develop the algorithms to efficiently retrieve the solution to search queries. I remember sharing this idea with a colleague of mine from IRCAM, Norbert Schnell, and he asked me if I was ready to spend the next 10 to 15 years of my life developing this idea. At first I laughed because I was eager to achieve my goal, but after we began I understood what Norbert meant. It is a huge project. But I would say we succeeded in the storage model. We study the state of the art of content-based retrieval, and we study several files format for music. Then we realized the best format was MPG7. It provides the necessary features to storage all the information we needed to solve the search queries as we thought. We also created a new data type for the Oracle Multimedia Database Manager. After that, we didn't want to give up entirely on the project, so we agreed on delimiting it. And that's how this project started. We thought a lot about what musical genre we wanted to work on. Since the city of Cali is called the Salsa's capital, we decided to focus on this genre. Um, so we have to change our objectives. Now we want to characterize the genre. We study many published work about salsa, and we realize every work about it has been made by men. I mean, there is no computational characterization of salsa. So we want to know what is salsa from a computational point of view. We want to know details about salsa, for instance, what makes salsa beat salsa. Is it the instruments, features like rhythms, melody, harmony, its lyrics, the singer or the band, anything else? Okay, in the next 3 slides, I'm going to explain some basic information about salsa. Salsa is a Latin American genre created by mixing an African and Caribbean rhythm with American jazz. The rhythmic element in salsa is called son clave, which is a sound made by a musical instrument, usually las claves, which is a percussion instrument composed only by 2 wooden sticks. The most common pattern is this. This rhythm is followed by all other instruments of the salsa band, especially by the piano or a guitar, which usually repeats a 4-band melody as an ostinato, like this. A salsa song is typically composed with this structure. The solo instrumental is called the mambo, and it is often played by the horn section of the band. There are 2 kinds of chorus in salsa. The typical chorus, where a group of 2 or 3 singers, the choir, sings a verse, and the call and response chorus, also called the montuno, where the lead singer sings some verse and the choir sings another in response. Let us notice the difference between the 2 kinds of chorus. First, the normal. And the montuno. Okay, so we split the project in 2 parts. First, we needed to build a data set, and then we can perform a data mining process over that data set using artificial intelligence techniques to answer the question we told you before. In order to build the data set, first we needed to find a large number of songs. We discovered that there are no public databases of salsa song. Luckily, we got 25,000 songs from private databases. However, since we got the songs from different sources, we needed to pre-analyze the songs, searching for repetitions, absence of metadata, etc. Then we can extract the audio features and metadata from the songs and finally add them to the dataset. We thought this was enough, but we found a problem. The algorithms we developed to analyze songs are not very efficient. Each song takes a lot of time to be analyzed. So we took a look at other data sets like the Million Song dataset and the Latin Music database, and we realized we don't need to consider the whole song, just a part of it. Most of these databases consider only 10 to 50 seconds of each song. So we decided to extract features from only 10 seconds of each salsa song. However, which 10 seconds? Some datasets consider the first 10 seconds of the song, others the last 10 seconds, other 10 seconds from the middle, or even in a random position. Then we realize the best part of a salsa song to consider is the one most repeated, that is the chorus. So we added a new phase in the algorithm to build the dataset. We tried to follow algorithms to discover the chorus of a song from various papers, but we failed. So we developed our own algorithm using cross-correlation. This algorithm works like this. We take the sound wave and extract the vector of peaks of amplitude. Then we split the vector in frames and perform a cross-correlation between them. The size of the frames is given by the peaks of the sound wave. But since we know for a fact that there are no chorus that last less than 5 seconds, we took frames of that size. We created a web page to share this dataset with the scientific community. We are convinced that this dataset can be used by the music information retrieval community. Students from our research team are happy to contribute. In fact, they are continuously adding more songs to the dataset. And we also want in the future to build an interface in order to users can upload their own salsa songs to the dataset. Well, on the part of the application of artificial intelligence techniques, we started using the software Weka and the algorithms of support vector machines, k-nearest neighbors, and decision trees. Right now, we are performing 2 tasks: clustering by discovering patterns in the songs, and classifications to know the cluster to which a song belongs. We could, for instance, group songs by the time of productions. Let us listen some extracts of songs from different decades. We may notice the difference between the songs from different decades. First, the 60s. A song from the 70s. From the 80s. From the 90s. From last decade. And salsa from this decade. Okay, sadly, this is not ground truth. We expect in the future to improve our models and achieve total accuracy. And talking about the future, after we finish the second part of our project, we want to continue the project in two directions. The first one is this. We want to compare our results with previous work and also perform experiments with human experts on our system. The second direction is related with dance. In our research team, we have one student which is semi-pro salsa dancer, and he is willing to model the evolution of how to dance salsa. The student will dance songs from different time periods in front of a camera and a keynet, and we will extract his movements and we'll try to discover patterns and make associations. And that's it. Thank you for watching.